learning about Schrodinger equation. Before we start with Schrodinger equation, we want to know what are the different terms associated with. The very first term is psi. Psi is actually nothing but a wave function which contains all the information about the wave. Now, the very basic thing which we know from our preliminary classes, that psi or the wave function for a particular wave can be written in the form ae to the power minus I divided by h cross into et minus px. Now the different terms here, as we know, are E is nothing but the time, energy, T is the time, P is the momentum, X is the position, and H is the Planck's constant. Now A is the amplitude. Now we have this wave function which has got this form. Now for any wave, when we talk about a wave, it has got some energy associated with it, right? So the energy is actually nothing but a combination of kinetic energy plus potential energy. So this particular thing is nothing but my total energy. Now let's see how can we write kinetic energy. Now kinetic energy, the expression, simplest expression that we know is nothing but E is equal to half mv square. So this can be written as half of m square v square divided by m. So we can write it as 1 divided by 2, and m square v square is nothing but p square divided by m. So it is nothing but p square divided by 2sm. Now let's just denote this potential energy with V. Then we can write that the total energy E is equal to nothing but P square divided by twice M into plus V. Now let's multiply both sides by psi, that is the wave function. So if we multiply that, we have this expression as E psi is equal to P square divided by twice M plus V of psi. Now we have this. Now let's see. Our aim is to actually find out what is Schrodinger's time dependent and time independent equation. So let's just talk about time dependent. Now when we talk about a time dependent equation, it obviously means that the Schrodinger equation that we finally derive is actually dependent on time, right? So we have this expression, as I've already written that for psi. When we use that expression and want to find out Schrodinger equation in terms of time, we can say that if we differentiate it once, then we have got del psi del t is equal to minus I into E divided by h cross into psi. Now from where we get this? We get this from this particular equation. So we have this from here. So we have a psi here, and then we take the differentiation of that, and then we basically find out what we call as del psi del t. Now what can I say? I can write my E as nothing but E is equal to I h cross del psi del t, or E psi is equal to I h cross del psi del t. So for your convenience, we already know that I square is nothing but minus 1. So if I have got minus I, it can also be written as I divided by I square, right? So we can write it as 1 by I. So we have this. Next, I want to find out the momentum term, that is P. So I want to finding out P and E. Now for momentum, what we do, we differentiate the same equation or same expression twice. So del square psi del x square is equal to minus of P square divided by h cut square into psi. We have this. Now when we just do a bit of modification, what we can say, we can have P square is equal to minus h cross square into del square psi del x square. Now we have an expression for P and E. So we have this, sorry, there is a psi here. So we have this. Now what we do, we actually want to replace it. So what was my expression? My expression was E psi is equal to P square divided by twice M psi plus V into psi, right? Now what is my E? E is nothing but minus plus I h cross del psi del t is equal to, now P square is nothing but minus h cut square, twice M is already there, and we have got del square psi del x square plus V of psi. Now this particular equation is what we call as the Schrodinger time dependent equation. So this is my Schrodinger time dependent equation. Now next I want to find out what is my Schrodinger's time independent equation. Now the Schrodinger's time independent equation. Now let's see how to do this. Now again I have got my expression as E psi is equal to P square divided by twice M into psi plus V psi. Now when we talk about time independent equation, this is actually not dependent on time. So what we can say that whatever psi we have got from the earlier expression, that can be actually replaced. So I have got a psi expression as a e to the power minus I by h cross into e t minus px. Now this particular thing can be actually replaced in the Schrodinger time dependent equation, and then we can get that expression. The easy way to remember is e, we don't need to change anything over here because it's just a psi, so it's not dependent on time. And this p square by twice m into psi, this can be written as minus h cut square divided by twice m into del square psi del x square plus v of psi. So this is my expression for Schrodinger time dependent form. You can just do a bit of modification here and just adjust it here. So it is h cut square divided by twice m into del square psi del x square, and then we can just take it that side, and then there is nothing but plus of e minus v into psi is equal to 0, right? Or even we can write it in this form, del square psi del x square plus 2m divided by h cut square into e minus v into psi is equal to 0. So this is my equation of interest, and this is what we call as the Schrodinger time independent equation. It is not dependent on time. Now since we've done this, now we want to actually know what are the cases when we talk about 3 dimension and 1 dimension. Now this is the case for 1 dimension. See, only the x expression is there, right? Whenever we're talking about 3 dimension, it's nothing but there will be del square psi del x square plus del square psi del y square plus del square psi del z square. So this is a simple thing. All x, y and z all will come into place, and then it is nothing but 2m by h cut square. So for convenience, we'll be actually doing some problems with 1 dimensional case. In the 3 dimensions, we can easily get back to that. That's not difficult. Now let's see what are the applications, right? Now what do you mean by a 1 dimensional box? You must have heard about that. It's also there in the syllabus. 1 dimensional potential box. Now suppose I'm trapped inside a room, right, and it has got a door somewhere here, suppose, and someone is there at the door, and he or she is holding the door very hard. So for me to escape through this door is actually very difficult. So what does it mean? That the potential outside is nothing but infinity, right? I cannot go out of the door. Suppose it's locked, then that's infinity, right? I cannot go out the wall, through the wall as well, so that is also locked, so obviously that's infinity. But inside the room I can move very freely. So what is my potential inside? Potential inside is 0, so I can move freely. So a box, when we talk about a potential box, it's something similar to this. Let's just consider, suppose an electron is actually trapped within this box. The dimension of the box along x-axis, say it is 0 to L. This is my x-axis. So outside the particle cannot escape, so it is nothing but infinity. Here also is infinity, but here it's 0, so it can move very easily here. So for a 1-dimensional potential box, in terms of expression, it might be written as V is equal to 0 when x actually lies between 0 and L, and it's infinity otherwise. So this is actually what we call as the 1-dimensional potential problem. Now an interesting part of this is, when we talk about this 1-dimensional potential problem, when we want to know what is psi. So suppose an electron is trapped here, what is the probability that the electron will be from this region to this region or to the entire region? What are the different probabilities that is present? Psi is nothing but gives me an idea about the probability of the existence of the electron as well, right? So it gives an information about the wave function. So let's just think about it. Now what we can do, let's consider the Schrodinger's equation. Now we are considering the Schrodinger's time independent equation here. So what is my Schrodinger time independent equation? As we've modified already, del square psi del x square plus twice m divided by h cut square into e minus v into psi. This was my equation, right? Now in this particular problem, always remember, in these sort of problems, first thing, at the boundary 0 and L, psi is nothing but 0, right? So psi doesn't exist, that the wave function doesn't exist, that means the particle doesn't exist, right? And obviously when v is equal to infinity, psi is equal to psi is nothing but equal to 0. These are the two things I need to remember before I start. Now let's see. Now I have got my v is equal to 0. I don't consider the second case because it's always meaningless, because psi is 0, so I'm not interested in that part. So let's just take v. Now v is 0, right? So what is my modified equation? Modified equation is del square psi del x square plus 2me by h cut square is equal to 0. So this is my equation. Now I want to solve this so that I can want to find out psi, right? So this will have a solution of the form. Let's write it in this way. Solution of the form, obviously this is psi term, and then we have got the double differentiation, so that it will have a sine term and a cos term. So psi is equal to a sine kx plus b cos kx. Now you might ask that what is k? Now we can write this in this form as well. This one, del square psi del x square plus k square into psi is equal to 0. Of course there is a psi here, I missed out on that. So it's k square into psi is equal to 0. So what do you mean? That k square is nothing but 2me divided by h cut square, right? So what is my k? K is nothing but root over twice me divided by h cut. Okay, now what are the things that I don't know here? I don't know what is a, I don't know what is b, right? But I know my k value, right? K I have already found out in terms of E and M. So I want to find out A and B. For this I will be actually using the boundary condition. Now what is boundary condition? Boundary condition, it means that at the boundary what is the case with psi. So first let's see at x is equal to 0. Now as I said, at the boundary psi vanishes. So at x is equal to 0, psi is nothing but 0, right? So when x is equal to psi is equal to 0, we can replace it here. Psi is equal to 0 and sine of kx, a sine of kx. So I put x is equal to 0. So sine of 0 is 0. So this is again 0 plus b into 1, right? Because cos of 0 is 1. So that means my b is equal to 0. Okay, so I get rid of my b. So what is my expression now? My expression is nothing but psi is equal to a sine kx, right? Now I'm interested to find out a. I've got rid of b, right? B is 0. Now next see what is a. Now let's use the next boundary condition. Next boundary condition is at x is equal to L, psi is again equal to 0, right? So I have got 0 is equal to a sine of k of L. Now I cannot have a as 0 here. There are two possibilities, either a is 0 or sine of kl is 0, but I cannot have a is equal to 0. If a is equal to 0, then the entire wave function becomes 0 and my entire task goes into water, right? There is no, it's quite meaningless. So let's see that what the other possibility. The other possibility is sine of kl is equal to 0. So from here I can say that kl is nothing but kl is equal to n into pi. So what is my k? K is equal to n pi divided by n, right? So what are the values that n can take? N is equal to 0, 1, 2, 3 and so on. So this n has got some physical meaning also. It is actually you can say it's defines the state. In which state is it? If it's the ground state, it's 1. If it's in the first excited state, it's 2 and on. Okay, so let's see now what happens. Now what we have my n as. So one of the expression which I have already found, k is equal to root over twice me by h cut. And the second expression just now I found out, it is k is equal to n pi divided by n. So if I equate these two, I have got twice me divided by h cut is equal to n pi divided by n, right? So if I just do a bit of modification to this, I can say that e squared is equal to squaring both sides, n square pi square h cut square divided by twice m into n square. So this is the expression for energy of that particular wave that is actually trapped in that box. So this is a very important expression. This is also needed for numerical problems. Right. Next, let's see what we getting up to. So we have got psi is equal to a sine of, now in place of k, what is my k again? Let's revise. N pi divided by L, right? So I can write n pi x divided by L. But still my a is unknown, right? Now always remember, psi alone doesn't have any meaning. It's meaningless, right? When we consider psi square, then it is nothing but psi modulus of square, right? This is actually giving me the probability of the existence of that particular wave. Now I want to find out what is the total probability. Now as we know what is probability, probability is nothing but the possibility of the existence of the wave in this case, right? So what is the possibility? Maximum possibility is 1. It cannot be greater than 1, right? It lies between 0 and 1. So obviously if we want to find out the value of A, we have to use this concept, right? So wave function with psi star. Now if I come back to this, psi star means it is nothing but the complex conjugate. So if there is an I, it converts to minus I. If there is I minus I, it converts to I. So it's just a real function. There is no imaginary part here. So I'm just writing modulus of psi square. So what is the existence? Now let's see its existence. Now existence can be from minus infinity to plus infinity, right? So is this. So what is this? Modulus of psi square into d psi. Now this must be equal to 1, right? So this must be equal to 1. That is the probability, and this is nothing but what we call as the normalization condition. It gives me an idea of the existence of the wave at the various regions. So let's just break it off. So it is minus infinity to 0 modulus of psi square d psi plus, now what's the next limit? 0 to L, I can say, and psi square d psi, and finally we have got as nothing but L to minus infinity modulus of psi square plus infinity, sorry, d psi is equal to 0. So what we can have here, this quantity is 0 because as I said the wave cannot exist here. This quantity is again 0, right? So what remains? Only this term remains. So I have got 0 to L modulus of psi square d psi is equal to 0. Psi is nothing but a sine of n by x divided by L, right? I know that. So if I just replace this psi here, 0 to L, a square sine square of n by x divided by L into d psi is equal to 0. Right? So it's very simple. You can use the expression of cos theta and the sin theta relation, and then you can find it out. So finally when you solve this equation, just to make sure that you know this, cos of twice theta is equal to nothing but 1 plus 2 sine square theta, right? So you can just replace this expression here and then we find out the relation. So what I have here is nothing but, finally solve it, a square L divided by 2 is equal to 0. Sorry, this is not 0, this is 1. So I have got a is equal to root over of L 2 by L. So this is my a. So this I have actually found out from the normalization condition. So what is my final expression? Final expression is nothing but psi is equal to root over of 2 divided by L sine of n by x divided by L, where n can take the values 1, 2, 3 and so on. So this is the thing which you are actually supposed to derive when we talk about a particle in a one-dimensional box. Okay, so with this expression I can find out the information about the particle, right? So this is the first thing. So let's just revise that what we have learned today. We have learned that Schrodinger equation can be either time dependent or it can be time independent, right? In the time dependent part, it is nothing but I h cross del psi del t is equal to minus h cut square divided by twice m into del square psi del x square plus v psi. That is the time dependent part. Now when we talk about time independent part, there is no time component here, so it is e psi is equal to, the right hand side remains the same, minus h cross square divided by twice m del square psi del x square plus v of psi, right? So next we have time dependent equation. Now next when we have the time independent and dependent equation, I want to know what is the application. So I have actually applied it in the Schrodinger equation, one-dimensional potential well. So if you consider a one-dimensional potential box, next we consider a one-dimensional potential box, and the first thing that I found out is nothing but the energy. Energy is nothing but E square is equal to n square pi square h cut square divided by twice m into L square. Please remember, we can also write this expression as E square is equal to n square h square divided by 8 m L square, right? Because nothing h cut is equal to h divided by twice of pi. Okay? This is the second thing that I've learned. And the third thing, the wave function for a Schrodinger equation, including using Schrodinger equation for a one-dimensional potential box, is nothing but psi is equal to root over 2 by L sine of n pi x divided by L. I hope you've enjoyed the lecture. Hope to see you soon once again. Thank you.